lecture here for about 35, 40 minutes and talk about the gradient potential which creates the threshold and opens a voltage-gated channel of an action potential. So if we are measuring, let's say you have the Physio X lab manual, and actually prefer the older one, the up to model, whatever, 8.0. Now it's 9.0, and 9.0 was rewritten. So I had to go back and rewrite the lab activities for the 9.0. So I have both 8.0 and 9.0 up here, so it doesn't matter which book you're using. If you're using 8.0, match that to the lab activity that you're filling out. And I prefer the lab activity 8.0 because one of the activities in there was the simulated testing of a sciatic nerve. And we have the all or none response for the action potential, that the minimum threshold current required to change and open the channels in a voltage-gated channel. It doesn't matter if the strength of the stimulus or the current goes higher than that. That channel won't open any faster, and it won't open any wider, and it won't open any longer. So the same amount of current will be produced each time. And I often reference this to an electric door at a grocery store or a department store, and those are either activated by weight or by breaking an optic signal. Okay? So if you're heavy enough to activate it by weight or tall enough to activate the optic signal, the door will open the same speed. If it's the weight, they don't want a little mouse running across, okay, or a rat running across the mat, causing the door to open in the early evening, okay? And yet they want somebody that's, say a 4-year-old, will not be locked out of the store because her mother was ahead of her. And so once the minimum weight is reached, then the door opens to the same degree as it does with somebody that's a full adult. So in our threshold, our voltage-gated channels, once that threshold current is reached, the voltage-gated channels open the same time every time, whether the current is twice as strong or 3 times as strong or just barely over threshold. And so let's say on this sciatic nerve from the frog, which is simulated for this experiment, we trigger it with an electrode and we send a current into this electrode. And so here's the resting membrane potential, and we give a signal, all right? And nothing happens, we get not nothing, but we get a graded potential. And then we increase the signal. That means a stronger signal, more current, and we get a stronger graded potential, but still we don't reach threshold. So we increase the stimulus strength again, and this time we get an even stronger current, and we open our voltage-gated channels and get an action potential. Now, according to the law of the all or none response, if we now form an even stronger potential, what should happen is exactly the same one as this. Okay, stronger current should not give us a higher or a bigger action potential. But if we do this to the sciatic nerve, you will get this. So how do you explain it? With that all or none response. Here's a hint.
Change in the threshold swelling.
You're on it here. She said a change in the threshold. So a sciatic nerve is not just one neuron. Correct? It's going to have thousands of neurons. It's not so much where it hits, it's that one neuron would have this threshold. And that neuron is going to fire the same way, even with this stronger stimulus. But there were 599 other neurons that didn't fire because we didn't reach their threshold. With a stronger stimulus, we reach the threshold of more of those neurons, Therefore, their culminative action potential current is stronger. Okay? So it's because we're talking about multiple neurons, the all or none rule is for one cell. And each cell is going to have its own particular threshold. The same is true with muscle. All right, so now let's go back and talk about just the example of one neuron. And here's the resting membrane potential. All right, over time, graded potential, not as strong, still subthreshold. Actually, I'm going to do this a little farther down here so I have more room. Still subthreshold. And now, finally, a current strength strong enough when it reaches the axon hillock to reach the threshold of our sodium and potassium voltage-gated channels. Okay? So this is a graded potential. All right? Created by the movement of positive charges diffusing down the cell body. When it reaches threshold, that particular current, the flow of charged particles, causes sodium channels to open. They close almost immediately. Potassium channels take a little bit longer to open, so by the time they're open, the sodium channels have closed, potassium channels open, and we have repolarization. These two components, and that's not a halo, depolarization and repolarization is what forms the action potential. Okay? So depolarization, we've covered that term already. Depolarization is due to the opening of voltage-gated sodium channels.
Bless you.
We gain positive ions. We actually move across 0 and typically into the plus 30 level when our cell depolarizes. Then we have potassium channels opening, and the cell repolarizes due to the opening of voltage-gated potassium channels. So that's what I have written here. Sodium closes, potassium channels open. We move sodium out of the cell, and potassium channels actually stay open a little bit too long, and we end up hyperpolarizing. Plus, we start our sodium-potassium pumps are now moving the sodium back out to reset the proper resting membrane potential, and so we end up losing a little bit too much of our positive ions, and so we end up with hyperpolarization.
And that's under the threshold.
Too far away from 0. So the action potential itself takes about 2.5 to 3 milliseconds.
Well,
That's 1/1000th of a second. Okay. And that's just for that one component there. This is just going over the movement of the ions. So these changes of the action potential, let's go back and look at those voltage-gated channels, and I have this in your lecture notes online. Looks like this page right here. page 11. So I have separate page 11. Mine is 11. If you printed off the 9, if you didn't print off the cover sheet. All right, so as we look at this, then we're starting at our resting membrane potential. All right, that's the flat line here on this particular cell. They have it at minus 90. We've been doing minus 70 and minus 55. So this is going to vary from cell to cell. All right, the inside of the cell has fewer positive ions than outside the cell. So we're at a negative resting membrane potential. The graded potential occurs. We reach threshold, which is the minimum current, and we haven't quite gotten there yet. So we're still at the resting membrane. And notice that the activation gate for sodium is closed, but at rest, the inactivation gate is open. And our potassium activation gate is closed. All right, so we're at a resting membrane potential because of our leaky sodium and potassium ions, because of our sodium-potassium pump, and the presence of proteins with their negative charges. All right, then the threshold is reached, and our sodium gate activation gates open. The inactivation gates were already open, and sodium starts to move into the cell. All right, more sodium channel gates open, and we see our spiking of depolarization. However, our potassium gates have not yet opened. Then we start repolarization. The inactivation gates in the sodium close, so sodium can no longer, and I don't like these arrows because it makes it look like the sodium is leaving. It's actually trying to get in and can't get in, but it makes it look like it's leaving the cell. It's just not getting into the cell. And potassium is now leaving the cell. So the cell membrane repolarizes, okay, as we lose positive ions. That's what happens with repolarization. We're losing positive ions. Right. Hyperpolarization, the potassium gates stay open a little bit too long as we kind of dip below. We lose a little bit too much potassium. Plus our sodium-potassium pumps have started to pump, and we're starting to get the sodium out to get back to our normal sodium levels, because if we keep sodium in there, we're going to get to the concentration level the same as outside the cell, and when we do open the sodium channels, the none will come in. So we have to move that sodium back out again. All right, and then finally we recover when the inactivation potassium closes, and then eventually the inactivation gates for sodium will open. Now, so on this review question, these sodium channels right here, don't look at the board.
Leaky. Oh, there's
Are what?
leaky.
So what, the sodium channels that are open at this point right here are voltage gated. All right? So on the resting membrane potential, leaky channels, leaky channels and sodium-potassium pumps are creating our resting membrane potential. They're always there, all right? But they're not creating the graded potential or the action potential. They create the resting membrane potential. Our threshold, this graded potential is going to be reached by ligand-gated, and additional leaky channels can contribute, and mechanically gated channels can contribute to our graded potential. But when we're doing our action potential, it is voltage gated. All right? So I want you to think of resting as leaky and sodium pumps, graded potential as ligand or mechanically. In the heart, we also use leaky. And then action potentials are always due to voltage gated channels. Yes?
Hyperpolarization is the part is like gated.
That's the first part is due to the gated potassium. The second part is due to the pump coming into play. Now, there's two more concepts I want to cover. One is the refractory periods, and the other is the Maillard sheath effect. So when we talk about the refractory period, a child who is refractory is a child or incorrigible, can't change. Okay, such as children and significant others too. There's a current musical going on, I Love You Now Change, or something like that. I've been hearing it advertised on the radio. So the effect that we're seeing along the axon, now that we've triggered this, is the current, the action potential is always traveling away from the cell body and towards the axon terminals, the synaptic boutons. When we actually think of it, however, and I'm just going to worry about one voltage-gated channel. All right, so when we open a voltage-gated channel, and sodium ions come into the cell, so many that our depolarization, our current inside the cell reaches a plus 30, do those ions only travel in this direction to the next voltage-gated channel? Is there any physical force? You're correct. There's no physical force that keeps those ions going in that direction. They are going to go in this direction as well. When I drop that rock in the pond, the ripples spread out in a circle, not just one direction. Okay? So the current, in actuality, is going to go in this direction and in this direction, as far as the internal current is concerned. However, upstream, closest to the cell body, are sodium channel is in this format. So if we go back to this slide, our sodium channel is closed. Okay? And this current going backwards doesn't open it. And that is called, during that time, it lasts while the channel is open during the depolarization, but it also lasts while that inactivation gate is closed. And so when it opens the next channel and the current comes back this direction, it is unable to open that inactivation gate. Okay? So this is called the refractory period. We cannot create another current. We cannot maintain the sodium channel open during the absolute refractory. It's going to open and close, and that absolute refractory period is going to last while so absolute refractory period lasts all the time that it's open, and plus when it closes, we cannot modify it, we cannot open it. And then it is in a relative refractory period for a short period afterwards, when it looks like this, when we can open it, but it takes a much stronger current, stronger than our normal threshold. All right, so during the absolute refractory period, we can't change, we can't make the channel say open longer, or if the inactivation gate is closed, we can't open the inactivation gate. In the relative refractory period, we can, but it takes a much stronger current to do so. Is our current getting stronger? So now let's say that the current is down here, and it's opening another channel. And this one is now going to be in this form. And this one will be in that, still in that form. So this is our resting membrane form. So why doesn't that, now that it's available, it's no longer in the relative refractory period, why doesn't this current from here open that one?
The stronger current, isn't it going to be pushed?
Because as the current is coming in and it's moving in this direction, is it going to stay stronger?
No.
As it travels that far, it's getting weaker and weaker. So by the time the channels are at the point where they are at resting membrane potential and it can respond to a normal threshold, the current is so far downstream that when it does diffuse back to it, it's too weak. All right? So the net effect is a series of action potentials that only propagate away from the cell body. And it has to do with the weakening of the current in relation to the time factor for relative and absolutely absolute and relative refractory periods. And that refractory period then maintains the current only going away from the cell body and not towards the cell body. So this diagram here kind of shows that in a similar fashion, but it's tiny, it's a little more complicated than what I just said. But essentially, it's the position and time relationship for how strong the current is when it gets there. All right, so the last point